students, welcome to Sunil's tutorial. I'm Sunil Milwani and today we'll be doing this chapter called as ionic. Let's see a derivation for hydrolysis constant. Now, we had already defined what is hydrolysis constant. Hydrolysis constant is the equilibrium constant which is obtained by applying law of mass action to hydrolysis reaction of a salt. Let us assume that Kh represent hydrolysis constant. Let us assume that Kh is a hydrolysis constant. Let us consider a hydrolysis reaction. Consider a hydrolysis reaction where you have salt reacting with water to give you base and acid. Right? In which case salt is Ba, reacts with water to give you BOH plus Ha. Right? Now, if I apply law of mass action to this, I can say dissociation constant is active mass of the product to the active mass of the base. Active mass of product BOH into HA upon active mass of the reactant BA into H2O. Right? Now, where I can say K is the equilibrium constant. Once you have this, then I can say that therefore K into H2O is going to be nothing but BOH into HA upon BA. Right? K into H2O. Now I can say that the concentration of H2O can be taken as constant. The concentration of H2O can be taken as constant because H2O is present in large excess. Because H2O is present in large excess and only a small amount of water takes part in hydrolysis reaction, and only a small amount of water takes part in hydrolysis reaction. Right? So in which case I can make you say that K into constant is equal to BOH into HA upon BA. Right? K into constant can be written as KH, which is nothing but BOH into HA upon BA, and this KH is called as hydrolysis constant. That's your equation for hydrolysis constant. Now, let us try to get a relationship between degree of hydrolysis and hydrolysis constant. Relation between degree of hydrolysis and hydrolysis constant. Right? Now, let's consider various types of salts. For this, let's first consider salt of strong acid and weak base. Salt of strong acid and weak base. Right? Salt of strong acid and weak base. Let us consider that we have 1 mole of salt Ba. Let us consider 1 mole of salt Ba dissolved in V decimeter cube of solution. Right? Let us assume that H is the degree of hydrolysis and let H be the degree of hydrolysis. Right? Now I can say that the equilibrium is represented as Ba reacts with water reversibly to give you BOH plus HA. This is going to be, I'm considering salt of strong acid and weak base. So this will be my weak base and this will be strong acid. Right? This is your salt in ionic form. In ionic reaction, salt will dissociate to give you B plus plus A minus plus water reversibly will give you weak, will not dissociate, strong will dissociate to give you H plus plus A minus, right? In which case A minus and A minus gets cancelled. So my net reaction will be B plus plus H2O reversibly gives you BOH plus H plus, right? Initial moles. Let's assume that we have already said that we are considering 1 mole of Ba. So initial number of moles of Ba is 1. Water is present in excess quantity. Reaction has not started, so there is no BOH, there is no H plus, right? At equilibrium. Since the degree of hydrolysis is H, I will get H number of BOH and H number of H plus ions, and the B plus ions will become 1 minus H and excess, water is still in excess. H number of molecules will dissociate, so the number of B plus ions that will remain is 1 minus H, and I will get H number of BOH ions and H number of H plus ions, right? Therefore, what will be concentration? Concentration is number of molecules per unit volume. So this will be 1 minus H upon V. This is still present in excess quantity. This is going to be H upon V and this is going to be H upon V. Right? Now apply law of mass action to this. I can say by law of mass action. If I apply law of mass action, I can say that dissociation constant is active mass of product. Product is BOH into H plus upon active mass of the reactant, that is B plus into H2O. B plus into H2O. Right? That is going to be my dissociation constant. Cross multiply. That means I'll get K into active mass of H2O will give you BOH H plus upon B plus, right? Once you have this, I can say but K into active mass of water is nothing but hydrolysis constant, right? Where I can say KH is hydrolysis constant. Therefore, I can say that KH is nothing but BOH into H plus upon B plus. Right? Once you have this, I can substitute the values. If I substitute the values, I get KH. BOH, we had found out active mass is H upon B into H plus, active mass is H upon B, B plus 1 minus H upon B. Therefore, I will get hydrolysis constant to be H, B and B gets cancelled. So you will get KH is equal to H square B, H square upon B into 1 minus H. But I can say that what 1 upon V is nothing but concentration. Therefore, I can say Kh is equal to h square C upon 1 minus h. Right? Now, also I can say that since h is very small, the degree of hydrolysis is very small, 1 minus h is approximately equal to 1. Therefore, I can say that Kh is equal to h square upon V, or because I am substituting the value of 1 minus h as 1, or I can say that Kh is equal to h square C. So that is my equation for hydrolysis constant. From this equation, what we understand is that the degree of hydrolysis of a salt of, I'm considering salt of strong acid and weak base, strong acid and weak base is directly proportional to the square root, is directly proportional to square root of, directly proportional to square root of dilution. How do I know this? Because we said that Kh is equal to h square upon V. That means I can therefore say that h square is Kh into V. Therefore, h is square root of Kh into V, where Kh is constant. Therefore, I can say h is directly proportional to square root of V. So what we understand is that the degree of hydrolysis of a salt of strong acid and weak base is directly proportional to the square root of dilution, or we can also say is inversely proportional to the square root of concentration. So in which case I can say that we have derived that Kh is equal to h square C. Therefore, h square is equal to Kh upon C. Therefore, h is equal to square root of Kh upon C. But Kh is a constant. Therefore, h is inversely proportional to square root of C. Right? So that is your derivation between degree of hydrolysis and hydrolysis constant for a salt of strong acid and weak base. Now consider a salt of weak acid and strong base. Salt of weak acid and strong base. Right? In that case, I can say let us consider 1 mole of Va dissolved in V decimeter cube of solution. Right? In which case, let us also assume that H is the degree of hydrolysis. Exactly like the previous generation, I can say that the equilibrium can be represented as Va combines with water to give you BOH plus HA. Now I am considering weak acid and strong base. So this is going to be my weak acid and this is going to be my strong base. This is salt in ionic form. In ionic form I can say this is B plus plus A minus plus water will give you strong base, B plus plus OH minus, weak acid will not dissociate. So in which case B plus and B plus will get cancelled. So I'll get A minus plus H2O will dissociate reversibly to give you OH negative plus HA. Right? Now, I can say that initial moles, let us assume that I have 1 mole. We have already assumed that in the beginning. Water is in excess quantity. Reaction hasn't started, so there will be no products. Right? At equilibrium. At equilibrium, degree of hydrolysis we've said H. So H number of molecules will dissociate. So the number of A minus molecules that will remain will be 1 minus H. Water is still present in excess quantity. H number of OH and H number of HA molecules will be present. Next, in that case I can say concentration. Concentration is nothing but moles per unit volume. So this is going to be 1 minus H divided by V. This is excess. This is H upon V. This is H upon V. Right? So in that case, if I apply law of mass action, by law of mass action, I can say that by law of mass action I can say K is equal to active mass of product upon active mass of reactant, A minus into H2O. Right? So in that case I can say that K into H2O is OH minus HA upon A minus, right? But K into H2O is nothing but KH. Therefore I can say that KH is nothing but OH minus into HA upon A minus, right? Now substitute the values. If I substitute the values, I will get KH is H by V into H by V upon 1 minus H by V. So I can say KH is equal to H square by V 1 minus H. Right? Now I can say but 1 upon V is concentration. Therefore I can say KH is equal to H square C upon 1 minus H. But as H is very small, therefore I can say that since H is very small, I can say that 1 minus H is approximately equal to 1. Therefore I could say that KH is equal to H square upon V. H square is equal to KH into V. H is equal to square root of KH into V. Therefore H is directly proportional to square root of V. Also I can say that KH is equal to H square C. 1 minus H I am taking as 1. Therefore I can say that C is equal to KH. No. I can say that H square is equal to KH upon C. H is equal to square root of KH upon C. H is inversely proportional to square root of C. Right? So from this what we understand is, hence the degree of hydrolysis, of a salt of weak acid and strong base is, first part, is directly proportional to the square root of volume, is directly proportional to square root of dilution, volume is dilution, and is inversely proportional to square root of concentration. Right? Next, let's consider a salt of weak acid and weak base. Let us consider a salt of weak acid and weak base. Salt of weak acid and weak base. So let us consider 1 mole of Ba dissolved in the decimeter cube of solution. Let H be the degree of hydrolysis. Right? In that case, I can say that the equilibrium can be presented as equilibrium can be represented as Ba plus water gives you reversibly BOH plus HA. Right, this is your salt, this is weak base, this is weak acid. Right, now in ionic form, I can say that B plus plus A minus plus water will reversibly give you weak will not dissociate, weak will not dissociate. Right? Just write this here again, B plus plus A minus plus water will reversibly give you BOH plus HA. Initial modes. You have H. Now you have taken 1 mole of the given salt, so 1 water is present in excess quantity, and this is 0 and 0. Reaction has been started. At equilibrium, degree of hydrolysis is H, so you will have 1 minus H, A will be 1 minus H, water in excess quantity, H and H, right? So in that case, I'll have concentration is number of moles per unit volume. So 1 minus H by V, 1 minus H by V, water in excess quantity, H by V and H by V. Now apply law of mass action. If I apply law of mass action, I can say by law of mass action, dissociation constant is nothing but BOH into HA upon V plus A minus into H2O, right? Where K is the dissociation constant. Right, now I can say K into H2O is nothing but BOH into HA upon B plus into A minus. Right? Now, but K into H2O is equal to KH. Therefore, I can say that KH is equal to BOH into HA upon B plus into A minus. Right? Now, substitute the values. If I substitute the values, I will get this as KH is equal to H by V into H by V upon B plus is 1 minus H by V into 1 minus H by V. Therefore, I can say KH is equal to H square upon 1 minus H the whole square. Right? Now, since H is very small, therefore I can say that 1 minus H is approximately equal to 1. Therefore I can say KH is equal to H square. Therefore I can say that H is square root of KH. right? From this equation we see that the term concentration or dilution is not contained in degree of hydrolysis. So if you have a salt of weak acid and weak base, then the degree of hydrolysis is independent of concentration and dilution. So I can say that the degree of hydrolysis of weak acid and weak base is independent of concentration or dilution. Fine. Okay, we will stop this here for the day. Thank you very much.